Hey everyone, I hope we're doing all right today. So what I'm going to go over right now is what's called the red rocket problem. And really, I'm going to kind of go through and explain a couple ideas about it. And so I have this rocket. It looks like this. It's pretty sweet. And so there's kind of this little slanted part here. And depending on which size of these wedges here, they have different angled sizes, the more this thing actually goes up and the steeper it gets. Now, for us today, it's going to be just laying flat on this bottom portion here, okay? And so it's just going to be launched straight up and come straight back down. So that's really kind of the main idea here. Now, you might want to pause, take a moment, write down kind of our three main equations because there's a couple assumptions, and we're going to make sure that these assumptions are valid. That's really the focus of this today, so that from now on, you kind of have these assumptions down, you know that they're legit, and then you can actually kind of start applying them and using that for the future, okay? So the main idea here is that the rocket is fired straight up and comes back straight down. So we're kind of neglecting the wind, we're neglecting it kind of blowing or being slightly angled. So we're just kind of assuming it goes straight up and straight down. And so right here, I have my rocket. Oh, that's a terrible rectangle. Maybe it can make a rectangle for me here. We'll see. Something like that. And then it has like a little nose cone. Yep. And there's a fin. There's another fin. Okay. And so the whole idea is that this guy here is actually going to get fired straight up. Oops. Here we go. And once he goes straight up, it's going to come back pretty much straight down. Something like that, okay? And so really, once he's straight down, and this is kind of a cheater move, sorry. Let's do that one more time. It'll be aiming straight back down, the same kind of orientation. Essentially, it really should be kind of right on top of where it was, but that just looks messy, so we're going to put it side by side, okay? And now we do get to call the bottom here y naught, so the initial displacement where it starts on the way up, okay? Or this could be thought of as the final displacement on the way down. So I'm not putting that little naught symbol because we can kind of think of this as two different trips. There's a trip that goes up and there's a trip that goes down. And so for the trip that goes down, well, the bottom here is the final displacement. It's where it finally ends. On the trip up, well, the bottom here is where it starts, okay? And both of those, though, are 0 meters. We're on the ground, all right? Now, we also do know that if it's going up on this trip up, that the final velocity on the trip up, well, that's 0. It stops at the top, right? But if we're thinking of it again as two different trips, we have a trip up, we have a trip back down. All right, don't trip. That means then that the speed it has up here at the top, we could think of that also as v naught down, the initial speed on the way down. So both of those are the same thing. The final speed at the top on the way up is the same as the initial speed for the way down, and both of those are 0, okay? So let me get my rocket picture out of here now. Clear this a little bit, kind of tidy it up. And so I want to go a little bit quicker, just to kind of hopefully kind of make sure that we go as quick as we can so I'm not wasting your time. And so we want to operate off of an assumption, and I'm going to prove this assumption. So assumption number 1. The assumption is that the initial velocity at takeoff equals the final velocity on the way down. So in other words, what I'm saying is that no matter if it's going on the way up or if it's going on the way down, when it reaches kind of this point, I'm saying that it's going the same speed. So one is going in the negative direction, one's going in the positive, but I'm saying that they're going the same speed. And so here's how we'll kind of prove this. I'll prove this to you, because we want to compare. Compare the trip up to the trip down. Okay, and so what I want to do is I want to use equation 3 here, actually. All right, so we'll kind of do a little division line here. We'll kind of look at the trip up on one spot. We'll look at the trip down on another spot, okay? So for the trip up, well, we'll say that this equation then is the final speed on the way up squared, and again, I'm using equation 3 here, is equal to the initial speed on the way up squared plus 2 times the acceleration in the y direction times how far it goes. So that's just the final y minus the initial y, okay? Now, we said, though, that at the top on the way up, it stops. So this final speed is 0, and we get to call the displacement where it's at on the bottom 0 as well, okay? So let's rewrite that. And we have 0 is equal to the initial y velocity on the way up squared plus twice the y acceleration times how high it gets. Okay, cool. So now, all I would like to do is kind of keep in mind that the acceleration here, really, right? The acceleration actually is negative because it's gravity. Gravity points down in the negative direction. So what I'm going to do is 2 things in one step. I'm going to subtract this over to the other side. So now we'll have negative the initial speed on the way up squared is equal to twice, and now we know acceleration is negative though, right? It's gravity really. So I'm just going to bring that negative sign out, okay? And then we have g and then y up, okay? And now I can see right here, well, we have a double negative, so the negatives cancel each other out. Okay, so now I have this weird kind of equation here. I'm going to circle it. All right, for the way up. All right, now let's look at the way down. So we're going to do the same thing. So the final speed on the way down squared is equal to the initial speed on the way down squared plus twice the acceleration in the y direction times the final y, on the way down minus the initial y on the way down. Okay, now let's look again. We have some things that are 0. The initial speed on the way down, when it starts going down, well, it's starting at the top. So it starts from rest because it has to stop and then starts speeding up as it goes down, 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 right? So then we also know that the final position on the way down is 0. So now this one is 0 instead. So now all we're going to do, again, is a little rewrite here, okay? So I'll kind of rewrite it now. So we have the final speed on the way down squared is equal to twice the acceleration in the y direction times, and then we have negative. So I'm going to bring a negative out here, and then our y displacement initially, okay? Because this negative totally still exists. So now I'm going to remind us that, well, the acceleration is gravity. It's going down in the negative direction. So we'll pull that negative out, okay? So now we have the final speed on the way down squared is equal to, well, we have a double negative now. So it's just 2g because the acceleration is due to gravity. This thing's speeding it up on the way down or slowing it down on the way up times our initial y position for our rocket, okay? So now what I want to do is really look at these two. The thing on the right side is the same, all right? We have 2g y down and 2g y up. Well, the final displacement on the way up, that's this y up here on the left, all right, is the same thing as the initial y for the trip down, right? So since the right side of each of these is the exact same thing, that means the left sides must be the same. So this proves to us, actually, since the right sides are the same, the left sides must be the same. So I can set my two left sides equal and say that the initial speed on the way up squared is equal to the final speed on the way down squared. So really I'm saying that no matter how fast it's going right here on takeoff is the same speed it's going upon landing, okay? And that hopefully is kind of intuitive, because if we think about it, every bit it goes up, gravity slows it down until it stops, but then gravity speeds it up just as much as it comes back down, okay? Cool. So we have the first thing. We have really that the speed is the same at the same position for it, really, okay? And so this tells me really that we have the same speeds, but opposite directions. Because since we're squaring it, y down can be negative, but since we'll be really like squaring it, it'll still come out positive, okay? So really all this is saying is that v up is equal to negative v down. One's going up, one's going down, one's going in the positive direction, one's going in the negative, all right? So now, assumption 2. Our assumption 2 here is that it takes just as much time to go up. It takes just, as much time to go up as it does to come back down. Now, there's a problem we do where it talks about a baseball getting hit up, and from the time it leaves their hand to the time it comes all the way back down into their hand, it's like 3.3 seconds. So this is what kind of proving that, well, however long it took for our rocket to make it up is the same amount of time it takes for the rocket to fall back down. We're going to kind of think about that, and hopefully that's maybe intuitive, but let's see if that actually makes sense, okay? So all we're going to do for this, so we're really going to use equation 1 now, okay? So we're going to use this guy. This is kind of the easier equation, I think. I think this is really the easiest of these 3 that we always kind of have to use. So we'll use equation 1, knowing that gravity does not change. Okay, so really I'll split kind of our page again here, and maybe we have like, I don't know, 5, 6 lines, something like that. And so we'll start for the up trip over here, as we just did earlier. So we have the final velocity on the way up is equal to the initial velocity on the way up, or really it's the speed kind of here, since we're kind of ignoring direction for the moment, except with our acceleration. All right. And now we know that at the top of the trip up, though, we said the rocket stops up here, right? So all that tells me is that the final speed on the way up is 0. Cool. So let's just solve for A, all right? So if I wanted to solve for A, I would subtract this initial speed up to the left side. So, let's go back to my blue. So we have negative V naught up, and then that would be equal to AT. Well, then I would just divide by T on both sides, right? So if I divide by T on this side, I divide by T on this side, well, the 2 T's here and here would cancel, right? And so really I can just leave it like that. All right, so that's it. That's my left side. Pretty simple, pretty easy. Let's look at the right side, which is the trip down. So we have the final speed on the way down is equal to the initial speed on the way down plus AT. And now if we look at our physical situation again, we said the initial speed on the way down is 0 because it starts at the top and it has to pause just for an instant before it turns around. So that tells us that this guy, come on. He can do it. Oh, I guess it's not letting me switch to black now. Oh, there we go. So that's 0. That's really all it's saying. Since it starts from 0 at the top because it's not moving, because it has to stop to turn around to start falling back down, we know the initial speed on the way down is 0. So this one's even easier. If I want to get A alone, all I'm going to do is divide by t. So again, I have that v down, our final speed on the way down, divided by our time is equal to the acceleration. Okay, so now what the heck does this mean? Why do we care about these simple looking little equations? So we're going to use what we did up here actually, because we know that the speeds are the same. So since we know the velocities, I'll use a fancy word here, are equal in magnitude, that just means size, and the acceleration due to gravity is the same, well, then t up really must equal t down. And I should have put some subscripts here. Really, this should be t up and t up, and this should be t down, and this should be t down. So really, all I'm saying is that we know this thing right here. We know v up equals negative v down. So in other words, what I could write then is I could rewrite this v down if I really wanted, okay? And just to really show this super explicitly, I could rewrite this whole thing then, and I could say that, well, v down, right, is just equal to negative v up, or really vice versa. I should have done it on the other side here. Sorry, let me fix that. Let's do it over on this side. So really what I'm saying is we could have rewritten this, and we could have written it, since we know that the speeds are flipped, okay, for this v naught up and v down. I could have rewritten it then as v down over t up equals a. Really, I'm just using this and kind of plugging it in right there, okay? So that's really what's happened here. And so looking at that, well, a is the same on both sides. V down is the same on both sides. And so if this is equal, that means that this little t up must be the same exact thing as t down. That's kind of what this is proving to us. Since the right sides are the same, they're both equal to a, well, the left sides must be the same. And so that means that our times must be the exact same value. Okay, that's really what this is kind of saying here, okay? So we know this one now. It takes just as much time to go up as it does to come back down. And so the final thing that we'll really write here, and then we'll be all done with these notes, is that the rocket is going the fastest at the bottom. The fastest at the bottom. All right. We also know that the time it takes to get to the top equals the time to fall from the top back down. Okay, so that's really it. And to summarize, just like what the heck we even did here, all we did is we really proved, kind of through some thinking and using these equations, we proved that the rocket is going the same speed at the bottom here, whether it's on the way up when it just took off, or on the way back down when it's just about to smash into the ground. All right, we know that it's going the same speed, just one is in the opposite direction. So their velocities are flipped. All right, but the speeds, the magnitude of the velocity is the exact same at the very bottom upon takeoff and upon leaving. All right, we also figured out that if I said it took 4 seconds to go from here all the way back to the ground, 4 seconds, well, that means it took 2 seconds to go to the top and 2 seconds to fall back down. We now can assume that that's true for anything kind of moving in the y direction. And later we'll find out that that's true for the y direction of things that are going off, not just left or right or up or down, but for things going at funny angles. All right. So that's it for now. Thank you very much.